非常抱歉把这个报告安排到早上了啊。这个我听学生讲说，现在的报告一般都安排在下午，这样保证大家起床后有时间听报告。这个早上的话呢，可能这个对大家起床来说有点压力。今天呢，我们这个非常荣幸的啊，邀请到我们的这个老朋友 Jeil 来给我们这个做个报告。我先简单介绍一下我们这个系列报告啊，这个咱们今天的报告呢是中国科大视乳为系列讲座，还有我们 ICQD 的学术报告的一个联合讲座啊。这个视乳为系列报告呢是为了这个纪念我们的这个物理系的创系系主任啊视乳为先生，然后我们命名的。那么呢，今天我们报告的这个报告人啊，他能听懂中文啊，我就先不用英文介绍了。他是在05年的时候呢，在西班牙这个获得了这个博士学位，之后呢，他就这个周游了很多地方，比如在台湾啊待了1年访问，应该是博士后。之后呢，从06年到13年呢，在这个 UT Austin 在那边做博后，到后来又做到这个research fellow， 做到 lecture， 反正战争的时间比较长一点，从06年一直到13年，完全把我在 Austin 待的4年全 cover 进去了。然后我们差不多同一时期就是离开UT Austin， 然后之后呢，13年以后呢，他又去了这个韩国的叫做 National University of 他去了不是韩国，去新加坡啊。我把那个 National University of Seoul 跟这个新加坡这个混了。他去在这个新加坡国立大学呢做了另外2年的这个 Senior Research Fellow， 然后到15年的时候呢就加入现在的这个韩国的这个首尔大学，这是他为了区分这个首尔国立大学，他这个叫做首尔市立大学，那个校园的环境非常好。当然我主要是从照片上看的啊。今天他的报告题目呢，这个还是关于这个石墨烯，因为Jeil以前其实我们合作了很多的工作，都是关于这个石墨烯的，尤其是他做了一些基于这个第一原理计算的这个转角石墨烯，这方面的工作这个引用也非常高啊，大家感兴趣的可以 search 一下他的这个相关的文章。今天呢Jeil给我们带来的报告题目是这个 layer pseudospin magnetism and electric field induced anomalous Hall effects in rhombohedral multilayer graphene 啊，那个叫做斜方菱形这个多层石墨烯这个体系里边。好，那我们以热烈的掌声啊，欢迎Jeil给我们做报告。
好，谢谢介绍。虽然邱老师说我还会说中文，我其实不敢报告，不敢演讲这个物理内容，所以我要 switch to English。But we can maybe 也许可以说到你的问题 in Chinese. Right. Okay. So as Professor Chao introduced me, actually one thing he didn't mention is that I was here already in 2016. So it was a very similar situation, but for me it is the first time I give a talk that is broadcasted in co-share. So it's a little bit, could be a little intimidating, but still I find it, I mean, I have many questions to ask you about this co-share business. So yeah, without further ado, let me briefly introduce the talk I'm gonna present. So as Professor Chao said, this is many of the content is going to be old work, because graphene has been around for many years now, since 2004, and actually for almost 20 years I've been doing research on graphene. So every time I wanted to move away from graphene, something new appeared, and so somehow I kept on working on the topic. So in some sense, it's going to be on 3 different topics: on rhombohedral n-layer graphene pseudospin magnetism, and then the notion of fractional metals, and the moire bands. So in some sense, this is a lot of content. So what I will be doing is just to give you some like summarized like overview with a few glimpses of the main notions I would like to talk to you about. So yeah, I get started with this notion of like pseudospin magnetism, and if you can understand that notion, probably that's the talk would have been a success. Okay, so this is a figure that you've seen many times probably. We have a very wide bandwidth of almost 20 electron volts, and the structure of graphene can be written in this like sublattice pseudospin basis, like a 2x2 Hamiltonian, where A and B lattices form the basis. The moment we add a second layer, the linear dispersion becomes quadratic. We can open up a band gap when we apply a vertical electric field by breaking the inversion symmetry. So this is a qualitatively different band structure from the linear dispersion. So what happens when we add more layers? Single layer linear dispersion becomes quadratic in a bilayer. It becomes cubic in an ABC trilayer. And when we have an ABA trilayer, we have combination of a linear dispersion and a quadratic dispersion. And again, we can represent all these band structures with this 2x2 like pseudospin like representation. And we can distinguish, depending on the number of layers, we have a different chirality, winding 1, winding 2. It just means that whenever we loop around this closed circle, the arrows wind once on the left case, and then the arrows wind twice on the right-hand case. So this kind of analysis was done by actually one of my colleagues back in UT Austin, Hong Min, now in Seoul National University. So he proposed this compact model for n-layer system, which is like an effective 2x2 Hamiltonian, where the winding number grows proportionally to the number of layers. So this is a representation of a like 5-layer rhombohedral multilayer graphene, which is one of the maybe star systems nowadays. And again, when you integrate out these internal degrees of freedom and you're left with only the outermost sublattices, you can do that by the second order perturbation theory. You can get all these different kinds of band structures that are dispersing more and more slowly as the number of layers are increased. So this will be, this fact will be of interest when we like study the multilayer systems. Sorry, so if you want to take a picture. So again, this is work by Hong Min. And so this was the paper in 2008 where he introduced the notion of pseudospin magnetism. So in fact, this part of the talk is going to be paraphrasing this notion. So what is pseudospin magnetism? So again, this is sublattice pseudospin, which is the same as layer pseudospin. And so this axis is representing on the x-axis the Coulomb interaction strength in this dimensionless parameter alpha. And then on the y-axis, we have the carrier density doping. So what this graph is saying is that in single layer graphene, you need a strong enough alpha to like open up a band gap in the system. Nevertheless, when you have a bilayer starting from j equal to 2, like any very small Coulomb interaction already brings about a phase transition to a broken symmetry order phase. So this is all what this graph is saying. And if you add carrier doping, somehow you need a stronger Coulomb interaction in order to bring about this order phase. So this is again a mean field approximation. And the point of this work was to say that the mean field pseudospin magnetism is a broken symmetry phase where you layer polarize or you sublattice polarize the system. So these arrows represent the pseudospin, like sublattice pseudospin arrows. So they're buried in the in plane. It means A and B are coherent. A and B sublattices, or they are layer coherent system where the carrier density kind of distribute homogeneously on both layers. But then if you look at the vicinity of the K point, they are pointing out of plane. So you can look at this as arrows that are trying to order in the same direction. But then when you get closer and closer to K, this winding becomes faster, the frustration increases, and then the easiest way for the electrons to order is to point out of plane. So when you have arrows pointing out of plane, I don't have a representation of the Bloch sphere here. You sort of move the charge from one layer to another. Okay, so that's the pseudospin magnetism. And that's kind of a ferroelectricity. So you spontaneously have charge going to one layer or going to the other layer. So that's essentially the mechanism. And here we have a breakdown of the total energy in different contributions. So this black representation is the total energy. And this green curve is the Hartree energy. Of course, this is the electrostatic energy that works against the ferroelectricity. But again, this Coulomb exchange is strong enough, and this is the intralayer exchange contribution, is strong enough to overcome all these penalties of the other contributions and stabilize this layer charge imbalance configuration. Okay, so this is essentially the main idea you have to keep in mind. And we also have to remember the fact that in graphene we have two valleys and two spin flavors. So we end up having so we end up having like 4 copies, like the 4-fold degenerate, and therefore it is possible that 2 components go to the top layer and 2 other components go to the bottom layer. So in that case, we would have a like charge balance configuration where nothing seems to happen, but then internally you have all these flavors like polarizing in the top and bottom layer, and that's the so-called like pseudospin antiferromagnetic configuration, which okay, so we'll get back to this a little later. Okay, so we can have this kind of broken phases, and in principle we can achieve. Okay, we can do similar calculation with the lattice model that considers the shape of the wave function, the lattice structure, and confirm that a similar trend still holds. So whenever we open up a band gap in like a chiral n-chiral Dirac system, we develop like a orbital moments associated with these finite Berry curvatures. And the theory we are using is at this point it's just Hartree-Fock theory, where the first term is the electrostatic Hartree contribution given by this expression, and the Fock term given by this other expression. These are like standard Hartree-Fock theory developed almost 100 years ago. So yeah, next year is going to be the anniversary of quantum mechanics, the 26th. And the 28th was Douglas Hartree, and on the 30th it was Vladimir Fock who invented these terms. And again, because of this 4-fold degeneracy, you can develop all this kind of pseudospin ferromagnetic, pseudospin ferrimagnetic, pseudospin antiferromagnetic, depending on the number of flavors that are polarized in which direction. So for the pseudospin antiferromagnetic phase, we have the charge balance configuration, For the ferrimagnetic phase, we have like 3 flavors pointing in one layer and 1 flavor pointing in the other layer. And this pseudospin ferromagnetic phase, we have a complete charge imbalance configuration. So this is a comparison of the total energy when we apply an external electric field. So obviously for 0 electric field, the best scenario is this one, the charge balanced like blue dots. But then whenever we apply a finite electric field, we progressively favor this partially like layer imbalanced, like a red curve. And when the electric field is very strong, we end up favoring the total, completely layer symmetry broken configuration. Okay, so this is more or less expected from intuition. And for that same reason, so we saw the charge balance, and here we see the band gap. The band gap, we have a like initially estimated band gap over 30 MeV within the Hartree-Fock theory. This is actually a very big, because the Hartree-Fock theory is not including any like Coulomb screening effect. But then the gap decreases when you apply an electric field. So somehow it starts increasing again when we have the partially layer imbalance configuration. And then at some point it starts closing again and going up again. So qualitatively, this kind of behavior was seen in a compressibility measurement by Amir Yacobi's group in already 2010, where we have a resistivity peak at the charge neutrality point. And then with the electric field, we can reduce that somewhat and then increase it when we make the electric field stronger and stronger. So this is a non-monotonic behavior that is pointing a Coulomb interaction driven order phase in this multilayer graphene system. And while this is a complicated table, maybe at this point, maybe you don't have to pay too much attention to all these minor details, but just keeping in mind that we can distinguish the contribution to the total hole conductivity by its spin or valley components. And then depending on whether the state is pseudospin ferromagnetic, pseudospin ferrimagnetic, or antiferromagnetic, we can have many kinds of different quantum hole contributions. And a similar, actually the same table in a more simplified manner can also be prepared here for n-layer, multilayer rhombohedral systems. Again, these like 3 configurations here represent the like layer balance configuration, where we have 2 flavors in one layer and 2 other flavors in the bottom layer. Okay, so this is the extension of the analysis we did for the bilayer system. In principle, should be applicable for multilayer rhombohedral systems. And in fact, it was like recently by this group at Shanghai Jiao Tong University, Chen Gurui, they sort of observed this peak of resistivity for 4 layers, whereas for a single, bilayer, and trilayer, the resistivity near the charge neutrality point is remain kind of small. And again, this is the plot of the resistivity versus electric field. This is the carrier density. So we look at the charge neutrality point, we see that the same non-monotonic behavior that we had, that Amir Yacobi's group had observed, but now instead of compressibility, we are looking at the resistivity. So we have a resistivity peak at 0 electric field that somehow becomes more conductive and again becomes more resistive when you increase the field. So in principle, I think this is a very interesting, like a correlated phase that deserves further attention in the future. But if you apply the same recipe for 4-layer graphene, then we can observe a similar phase diagram when we have a dwindling a band gap that increases again, decreases again, and increases again as a function of electric field. And then here we have again the crossover of the layer antiferromagnetic phase, like the charge balanced configuration that eventually becomes the valley Hall and layer polarized phase. Okay, so qualitatively this is quite similar to what we already had found for bilayer graphene, only that experimentally it showed much more clearly. Whereas in bilayer, actually those features were extremely small, on the order of a few milli-electron volts. And for these kind of simulations, it turns out that the hopping parameters that are used in the tight binding model, for example, these are like transferable hopping parameters that reproduce the DFT-LDA calculations, turn out to be sensitive and important. So this is an analysis we had done for trilayer graphene, where this is the band structure without any remote hopping term. So you get a circular bands near the K point. And depending on the value of these gamma 2 or gamma 3 terms, gamma 2 represent this like vertical hopping, and the gamma 3 represent this type of hopping term. We can introduce like trigonal distortion of different signs, and it turns out that depending on the signs you choose, you can suppress the gap or enhance the gap substantially. And for many years, I think more than like 95% of the papers were using like incorrect signs for the gamma 3 sign. And somehow it didn't matter very much. But when you start looking at the fine details, this starts playing an important role. So that again, I mean, so then we corrected that in this paper, and okay, this is again maybe just ab initio calculation detail, but sometimes these kind of details are important. Okay, so this was for the first part. For the second part, let me again just try to focus on a few core ideas and maybe glide through the details. So what happens to these order phases when you open up a gap in the system initially, and then you carrier dope the system afterwards, and you open up a band gap with an electric field? So then you get like metals that valley or flavor polarized. So that's a summary of what I want to tell you. So again, rhombohedral multilayer graphene is a like interesting system. So in this P1, P2, P3, and P4, we are showing the number of flavors that are polarized when we carrier dope the system. So in P1, we increase the carrier density and we are filling only one of the flavors. For P2, we are filling 2 of them. For P3, we are filling like 3. For P4, we are filling the 4 of them evenly. So in principle, you would expect that when you carrier dope the system, you would find normally this scenario where you fill all the flavors simultaneously. But it turns out that in theory and also in experiment, you can reach this kind of like time reversal broken symmetry solutions due to Coulomb interactions. And that's was first observed in ABC trilayer graphene. You see different regions of different like flavor polarization. You can see that through the Shundikov-de-Haas oscillations that can count the number of Fermi surfaces in the system. So this was the experimental observation, and it was observed for 2 layers, 3 layers, 4 layers, and 5 layers. But then, of course, in the chronological order is first for 3, maybe, and then for 2, then for 4 or 5. Actually, I don't know which one came first in these 2. Probably 5, 4. And again, this is the work by Zheng Guorui's team. but again, for 5 layers, you get also very, very clean features. And again, these are like the different experimental results. They are showing different things in these color plots, but essentially the y-axis is the perpendicular electric field, and then the x-axis is the electron density. So for all these systems, you can observe this kind of flavor polarization and like a host of very interesting order phases, broken symmetry phases. And again, so this is again an old work already published like 9 years ago, where in the Hartree-Fock calculation, if you carrier dope the system slightly, you would develop this kind of nematic phase, which is valley polarized. This is like Hartree-Fock calculation. And when you increase the carrier doping, the nematicity disappears. So you get like this kind of annular Fermi ring shape. And for this reason, in principle, you could trigger like a finite Hall conductivity. That when you again, this is the x-axis is the carrier density, the y-axis is the Hall conductivity. The Hall conductivity would increase and then eventually drop to 0 when the carrier density is high enough. And so this kind of like qualitative analysis shows the difference between like a single, like a Fermi circular Fermi surface and a Riemann surface, where in principle this kind of shape favors like occupation of states that are concentrated in a corner of the Brilliant zone. And somehow this is an idea that was also discussed by Heisenberg and also discussed by Fritz London in their attempt to explain superconductivity already many years ago. Of course, I mean, this is an old theory that has been superseded, but then the notion of the exchange interaction driven, let's say, momentum space condensation was the notion they had introduced, and it just means that the Coulomb interaction, the exchange interaction, tries to bunch together states that are close by in momentum space, and that's because the exchange, like self-energy or kernel, is peaked for at Q close to 0. And so energetically, we would naturally favor flavor polarization if this like a energy curve bends downward, and it would favor like even no polarization when this energy curve bends upward. Okay. So this is an analysis that we refine by just carrying out the correlation energy within the random phase approximation. This is just to include the screening effect at a further level. And again, this is a complicated figure, but then let me just focus on this pictorial representation. So we distinguish here 3 different fillings. Like this is the Mexican hat structure, and then here we have a ring shape, and here we have a like a Fermi surface and a Fermi dot, and then we have a like a single Fermi surface. So here, what I'm trying to represent, again, this is the x-axis is the carrier density, and then the y-axis is the electric field. And so this is the phase diagram where we have P1, P2, P3, and P4. And these lines are, these dotted lines are the lines where we have the transition when we cross this this point of the top of the Mexican hat structure. So it just means that this ring shape strongly favors the flavor polarization. Therefore, the moment we cross over, we strongly tend to have a phase transition. So that's what we want to say with this breakdown of the total energies in the different components. So that's why these phase boundaries somehow are close to these dotted lines. Okay. And again, this is a more detailed breakdown and the energy comparisons between the P2, P3, P4 along this line and along this other line. And again, the take-home message is that the moment this Fermi surface, Fermi level crosses the top of the Mexican hat band structure, then that's more or less where we have the phase transition. And here we have a comparison of the experiment with theory. And somehow, let's say here we use the dielectric constant of 2.5. And somehow, at least the order of magnitude is comparable. Although, again, there are features that are not, don't agree with experiments. And again, that's because this theory ignores the remote hopping terms, and probably because of some other elements that are missing in the theory that should be investigated further. Okay, so okay, maybe I'm going too fast.
It's okay, no problem.
Right. And finally, let me talk a little bit about the topological moire bands in this rhombohedral system interface with hexagonal boron nitride. Again, this is an experimental result in a trilayer graphene, where one of the HPN surfaces is almost aligned, almost at 0 degrees. So this is an experiment where the top gate voltage and back gate voltage. So this diagonal represents the strength of the electric field, and this other diagonal represents the carrier density. And this bright color represents the higher resistivity. So it means that we are at the charge neutrality. When we increase the electric field, we open up a band gap in the system, as we normally expect in rhombohedral multilayers. But then when we have a metallic system, in principle, we shouldn't increase the resistivity. Nevertheless, you see a peak in resistivity. So, for example, this one. Then it is assumed that that's due to Coulomb interactions. And how do we understand that? Okay, so we go back to this representation of the superlattice. Moire superlattice generated by this hexagonal boron nitride substrate. So we again use this 2x2 Hamiltonian for the band structure. This is the interlayer electric field, remote hopping term, and in addition we use this Moire potential. And then let's see how the band structure changes. So this is the band structure of trilayer graphene without anything. And then with an electric field, we open up a band gap at the charge neutrality point. And here is the band structure when you have a HPN that is aligned. So you avoided gaps here at the superlattice, Dirac points. And with an electric field, with a combination of both effects, you can lead to an almost flat and isolated band structure, where the bandwidth is, let's say, of the order of 10 or 20 millielectron volts. So that's like 1,000 times flatter than the 20 electron volts we talked about in graphene. And so in this case, you have the advantage that even for finite twist angle, you can achieve this kind of very narrow bandwidth. So unlike twisted barrier graphene, where you have to be very, very careful with the twist angle. So here you have a very wide range of twist angles where you can achieve this kind of flat bands. And another interesting fact is that these flavor separated bands are topological. So this is a very interesting fact due to the isolation of the band, and which has been therefore a subject of active research. It means, for example, if you have this fourfold flat band, and depending on the filling, if you sort of can independently fill one of them, you can already generate like a quantum Hall effect associated with that, with the topology of the band that is occupied. Okay, so this is like a very interesting way to achieve like topological phases, and in fact, this was observed in experiment by this Feng Wang's group in Berkeley. Only that the observed like Hall conductivity turned out to be a little different to what was expected for a trilayer. You get like Hall conductivity of 2 units instead of 3, and so this is a plausible explanation that when you develop a nematic phase or you break the rotational symmetry, it is possible to achieve a phase transition from c equal to 3 to c equal to 2 like a situation. Okay, this is one of the plausible explanations. And likewise, you expect like similar behavior for multi-layer system, 4 layers. And these are the phase diagrams for 4 layers, but then you similarly expect for 5 layers and 6 layers. And these are like the different moire bands and moire band structure for 3, 4, 5 layers. And for this kind of systems, again, depending on the alignment of the HPM with the multi-layer rhombohedral system, you may develop like Chern bands with Chern number 0 or Chern number equal to 1, depending on subtle details of the Hamiltonian. So, and this is important because, so this is an observation of the fractional quantum anomalous Hall effect by Jeil's group at MIT, where they observed this development of this fractional Hall effect, and for that, in principle, you need, well, you would expect to have a like Chern band to start with, and this is like a proposal by like Li Xiao in Hong Kong City University, Shankar Sharma and Zhang Fan, where in principle you don't have naturally an isolation of the conduction bands in pentalayer graphene on HPM, but then when you have Hartree-Fock Coulomb interactions, you may somehow develop this kind of band isolation. But again, this is, I think, a topic that deserves further attention. And so again, this is an attempt that we are doing in our group in order to try to improve the description of the rhombohedral multilayer graphene's band structure. We mentioned that subtle details may end up playing a role. So this is a calculation where we add U and V correction to the band Hamiltonian, enhancing the Fermi velocity and also changing a little bit the hopping terms. So this might be used also in the future for further research. Again, so this is the summary of the presentation. I think I told you many things. It's a lot of content, but again, I wanted to sort of bring up a few essential ideas on the pseudospin ferromagnetic phases, on the notion of these fractional metals, and the fact that you can develop like topological flat bands in moire systems, which by now maybe is a well-known fact. But then we can, with this, we can open some discussions or later after the talk. Okay, with this, yeah, thanks for your attention.
Thank you. Very productive results, and In this talk, Jeil has talked from a bilayer to 5 layers, right? And consider kinds of interactions. And, you know, from the first discovery of monolayer graphene to now it's over 20 years. Graphene, multilayer graphene devices or systems are still so hot. And there are so many new physics emerge. I think that's a miracle. Okay, welcome questions from students and teachers. Any questions? Hi, Qingwei.
Yeah. So can you expand a little bit why the nematic phase have turn number 2, while the symmetric phase has turn number 3? What happened there?
Well, actually, okay, so this is just result of calculation in some sense. So in principle, the turn number 3, you could say it is somewhat natural to expect like turn number 3 in a trilayer system, because the winding of the pseudospin fields like increase proportionally with the number of layers, and somehow the gaps you open at finite energy due to the moire pattern somehow is not changing, is not flipping that behavior. So under that assumption, you sort of can justify that's somewhat natural in this kind of trilayer systems. But then for actually for the nematic phase, we haven't in this work we haven't found a microscopic explanation, but just the calculation adding a off-diagonal like pseudomagnetic field that somehow distorts the like rotational symmetry, somehow is able to close the band gap and again reopen it further. So we tried many different types of external potentials, but then the off-diagonal term turned out to be somewhat the essential part. And with that, you nearly always break the rotational symmetry of the system.
Okay, thank you. So can I ask another question about the so you mentioned that the Hartree-Fock Hartree-Fock calculation overestimate the band gap, right? And you also have done some correlation effect correction to the total energies, for example. So do you think in your calculations have you if you take into account the correlation effects, does this effect will help you correct or reduce the band gap, Hartree-Fock band gap? Or are there approaches or method we can employ to give a more correct prediction of the band gap?
Certainly, it would be quite interesting this to do the calculation at the RPA level. I don't think there are many such calculations in the literature, because yeah, you have to sort of concentrate. You have a very high k-point sampling near the brilliant zone where you sort of should see the order phases. And so actually, I'm not aware of such calculations. I think there is a group by Matteo Calandra. They claim they have done like a very high k-point density DFT calculation at the Hartree-Fock level, but then with some effective screening effects. Yeah, that's the calculation I'm aware of. But then, yeah, certainly the band gap would reduce drastically. And in fact, actually, so this is a calculation with a spontaneous gap using this extended Hubbard model, considering only these were on site and then V1, V2, and then the band gaps again for like trilayer, it essentially doesn't open up a gap, and it starts opening from 4 layers onwards. Whereas my initial calculation estimated like 30 MeV for bilayers, but then in experiment, the gap was 1 MeV or 2 MeV when you suspend the samples. So there's a huge, like, order of magnitude change.
Okay.
So here you show how to tune bands, like how you can have like flat and trim bands, and I think at the end you mentioned that it's a good starting point to further study like the fractional trim bands. So I think in the beginning when you try to get these trim bands, you already add like the Coulomb interaction, right? So when you further, I'm kind of curious. So if you want, if you further want to get this fractional trim bands, so since at the beginning you already added the Coulomb interaction, so how like get your way like from trim bands to?
For this discussion, you should talk to Li Xiao rather than myself, because this is their claim. And so in fact, of course, this is something in the ab initio community people are doing all the time. For example, in the GW calculations, you already have like interacting phase, but then the GW calculation are based on the DFT, LDA, or GGA calculations, which already somehow includes the interaction in the exchange correlation kernel. But then with the GW, you add some many-body effects, again described with quasi-particles, weakly interacting quasi-particles, and then on top of that, you normally do like excitonic calculations. So somehow, certainly there will be double counting of the Coulomb interaction effects.
Okay.
But then you need to somehow start. You normally start from a single particle basis or a quasi-particle picture of weakly interacting systems. And there you do the like exact diagonalization of the strong correlated. So of course it could be controversial.
Okay, so basically there are more channels, right? So the channel you get like the trim band phase can be different from that you get the fractional trim bands. You somehow add more channel units.
Mm-hmm.
Okay.
Yeah. So yeah, I think this is a topic that yeah deserves some further attention.
Okay. Thank you.
Mm-hmm.
Okay. Any questions?
Thank you for your talk. You have mentioned the in a big table the antiferromagnetic system. They can have a non-zero anomalous effect. So what's the mechanism of this phenomena? In page 14. Yeah.
Okay. Yeah, this is work that we did a very long time ago. So yeah, Professor Niu Qian is here. Actually, we yeah, 你好. Yeah. So again, yeah, this is the work that we Zhang Fan, Professor Niu Qian. Again, okay, this was like the non-interacting picture, and then again with the Hartree-Fock calculation. Again, you can always argue whether is Hartree-Fock enough. I mean, there are many people who wouldn't agree with that. But again, in this case, when you sort of consider like coupling between K prime and K, somehow energetically you favor the layer antiferromagnetic phase a little bit. The intervalley coupling is kind of small. Otherwise, within the Hartree-Fock level, you cannot distinguish. They are completely degenerate. But then the intervalley exchange coupling favors the non-quantum anomalous Hall effect, their antiferromagnetic effect. And then there was a paper by Rahul Dankishore where he proposes that quantum fluctuation somehow favors the quantum anomalous Hall effect. Published almost at the same time. But at the Hartree-Fock level is the layer antiferro which is favored. We haven't included the Coulomb interaction, Coulomb correlation effect beyond Hartree-Fock in our theory. It's also a very interesting research for the future. All these broken symmetry phases is still yet to be seen whether they are real, just layer antiferro, or they're something else. I think there might be something else. For writing the paper, we sort of went to the simple picture.
Okay.
Let me ask you a question. I find this pseudo magnetic field concept is very exciting. You know, especially together with the interaction effect. Okay, and the pseudo magnetic field, I think it belongs to a concept where well, how to say, it's a you know, the usual density functional theory is based on the charge density, all right, but there's a variant of the density functional theory called the current density functional theory. Okay, which treats the effect of a magnetic field, orbital magnetic field, I think including this pseudo magnetic field. I think it's an orbital, right? But have different signs for the different values. I think it might be interesting to look into the current density functional theory, see how the pseudo magnetic field, you know, gets normalized by the interaction effect.
Yes. I think
so. So, is there some study in the literature on this line?
Well, you know, I wouldn't dare to. I haven't actually searched in the literature well enough. Maybe there is something. I think some people have tried separating the values artificially. For example, in the density functional theory, distinguish the density coming from K valley and K prime valley, and make a effective interaction model somehow that distinguishes valley. I think I have seen such attempts, at least in conferences, not in the paper yet.
Okay,
but
not
based on the current.
Not the current density functional theory.
So the pathway you propose might be a very interesting.
Yeah,
way
the guy
naturally.
who drive this idea, I mean, it originally was a Italian guy whose name is Giovanni Vignali, who used to actually collaborate with a paper by Zhou Dishao, myself on this magnetization formula. So I think it would be interesting to look into this.
Yeah, it would be an exciting direction, especially.
Yeah, especially, you know,
all these orbital magnets.
Especially, you know, all these Chern bands, right? And or fractional Chern states are all based on this pseudo magnetic field become very become a very important concept. It would be nice to have a rigorous framework to re-examine how that concept renormalizes by the interaction.
Yeah, thank you for this very interesting comment, and because I think it's a very nice point that you make.
Any more questions? Okay, let me conclude. just I just saw the several pages discussing the fractional quantum anomalous Hall effect, right? And the fractional quantum anomalous Hall effect have been experimentally observed by several different groups. Actually, such kind of a concept was proposed by Professor Tian Yu about, let me see, 14 years ago. In 2010, when we published the paper, Quantum Anomalous Hall Effect, I remember Professor Niu asked me, where is it possible to find the fractional quantum anomalous Hall effect? I said, no, it's not impossible. But for the monolayer graphene, right, it is really impossible so far. But when we turn to different multi-layers, we forgot the question. If we remember the same question, I think that we should have done something. And so. Yeah.
She actually tried something.
I see. Okay. Anyway, thank you, Jeil, for your very exciting talk, and we welcome you to visit us in the next years or months, and